Okay, so hi everybody, and welcome to the new session of our agent-based modeling for policy seminar series. Today we have with us Jiri Kukacka from the Institute of Economic Studies at Charles University in Prague, and who will present his work on estimation of heuristic switching in behavioral macroeconomic models. And well, I'm sure those of us having gotten our hands a bit dirty with the task of estimating and calibrating models will very much appreciate the topic, which is indeed at the heart of some of the challenges faced when trying to bring agent-based models to speak to the data, right? As always, please do keep mics closed, except for asking questions. Clarifying questions are most welcome during the talk, and probably questions about details, it might be better to leave them for to the end, so as to allow the speaker to advance. And with that, Jiří, floor is yours.
Good afternoon. Good afternoon to London. Good afternoon to Madrid, and of course to everywhere else from where you connect. My name is Jiri Kukacka, and I will today present our paper entitled Estimation of Heuristic Switching in Behavioral Macroeconomic Models, which is a joint work with my co-author Stefan Sacht from Kiel University in Germany. Before I start, actually, I would like to direct your attention to the chat, where I put the link for the download of this paper, because when preparing for this presentation, we actually found some typos, which we immediately corrected. So especially if you are interested in this talk at the level of technical details and you have the version from February, please go to Social Science Research Network and download the most current updated, hopefully typos-free version, which is dated March 19. That's the first thing. The second thing I would like to mention before I start with the details of the paper is just a short notice or short note. The paper is after revision, and it has been resubmitted to the Journal of Applied Econometrics. So please, if you can, cross your fingers for me and for Stefan for the resubmission. Before I click the second slide, I would like to explain the title, actually, to set up the expectations, because we all know that expectations are crucial in economics. So it will be about estimation, it will be some econometrics, it will be about estimation of behavioral macroeconomic models, which I think I can suggest that it's a subclass of agent-based macroeconomic models. And it will be focused on the phenomena of heuristic switching of boundedly rational heterogeneous agents between a set of forecasting rules of thumb. This is it, and we can start with some details. So to explain a bit the title in details, so if I talk about behavioral macroeconomic models, I basically think about the tradition of three equations, so-called behavioral Nuke model, which actually takes into account the heterogeneity of agents. And these agents can select from or adapt simple heuristics, simple behavioral rules of thumb in their forecasting of macroeconomic variables, namely output and inflation. And the tradition of this behavioral Nuke model dates back to 2010, let's say a decade back, when this idea has been introduced by Bill Branch and Bruce Mayhew, together with Paul de Grauwe from LSE. The two most recent contributions are again actually by Paul de Grauwe and Ji. The first is the very nice, I highly recommend, a very nice book called Macroeconomic or Behavioral Macroeconomics Theory and Policy, which has been published by Oxford Publishing in 2019, and a new paper published in the European Economic Review in 2020. So basically, we follow this tradition of behavioral Nuke engine modeling, and why this model is so appealing. The first reason is that we can call this model a simple agent-based model because it really takes into account the notion of heterogeneity of agents. And what is also important, compared to a standard Nuke engine model, this behavioral model is able to replicate some empirical stylized facts, empirical features of the US macroeconomic data, especially the high persistence of the output gap and fat tails of the US output gap. And this was impossible. This was impossible in the standard Nuke engine model, and the Nuke engine model had to be somehow extended, and it had to be fueled by AR1 shocks to be able to produce this behavior. And the behavioral Nuke engine model is able to replicate this behavior even if it is only fueled by independent, non-autocorrelated Gaussian shocks. So this is one of the magics of the behavioral Nuke engine model, that based on a Gaussian non-autocorrelated shocks, it is able, via the endogenous dynamics of the model, which is based on the interactions of the agents inside the model, replicate the empirical features of the US data. The second key term of the title was heuristic switching, and perhaps a lot of you know what I will be talking about, but I will rather be a bit more specific what this means. We understand the heuristic switching as very important, maybe a crucial feature of the macroeconomic modeling strategy, because it allows for so-called bounded rationality of economic agents, which is something which I hope we all feel it's a pretty realistic description of how economic agents actually behave. And it offers a tool, a mathematical tool, how to incorporate a set of simple decision rules, simple heuristics, from which these boundedly rational agents can choose from. If you are familiar with financial agent-based models or financial heterogeneous agent models, very often these heuristics or these decision rules are pretty simple. Very often there are only two: the fundamentalists and speculators or chartists. But for the macroeconomic model, we can have a broader menu of forecasting heuristics, and for our application, we actually decided for the, again, based on one of the most recent contributions by Kaz Holmes and his co-authors from, again, the European Economic Review 2019, the menu of heuristics, which are called the adaptive heuristics, the trend following heuristics, and the anchoring and adjustment heuristic. Theoretically, there can be more, then everything is much more complicated. So because of this very recent publication, and because these heuristics are very well micro-founded, we decided to follow this set of heuristics, which the agents in the model have on the menu. And the agents have to somehow decide which heuristic will they follow at a given point of time in their forecasting efforts to forecast next period inflation or next period output gap in the model. The key feature, and this is the key dynamical feature of the model, is that the agents can switch between these heuristics, and naturally the heuristic which is the most accurate, no matter which one or which of those it is, but the most accurate heuristics will naturally attract the most attention of the economic agents. So there will be a large fraction of the agents who follow or who behave according to the heuristics, which is the most accurate, and only a few agents will behave according to heuristics, which is not really accurate at a given moment of time. This can be very simply measured by so-called mean squared forecasting error or mean squared forecast error. And the model dynamics of this switching is driven by so-called multinomial logistic or multinomial logit formula. This logistic formula for the heuristic switching goes back to the early papers of Carl Holmes from 1997 and 1998, where they introduced this multinomial logistic formula to asset pricing models. And for those who are not familiar with this idea, I prepared a simplification of the principle, and I hope, although this guy is a bit ugly, you will be able to get the gist of it very simply. So have a look. The agents, no matter whether they forecast inflation or output gap, they have this menu of 3 heuristics. And although we do not know the formulas yet, I believe that it's pretty clear what is the idea of these heuristics just based on their names. So we have a unit population in the model, and this unit population needs to be divided, or the agents need to sort themselves into fractions based on or into groups, and in each group the agents follow one of these heuristics. So if we focus on this adaptive heuristic, we can compute a fraction of agents who take into account the adaptive heuristics as the ratio between the e to the power of this guy divided by a sum of e to the power of this guy again for each of the heuristics. So basically for the adaptive heuristics, we only take into account the mean square forecasting error for the adaptive heuristics, and we divide by the sum of these guys, which take into account the mean square forecast error of all 3 adaptive, trend following, and anchoring heuristic. These fractions sum up to 1, so each agent has to follow one of the heuristics. This minus needs to be here because the mean square forecast error basically follows the principle that the lower the better. So that's why we have minus here. If you are used to financial agent-based models, we have plus here because the performance measure of the heuristics is often a profitability. But now we would like to have as small forecasting error as possible. And what is crucial is this parameter gamma. This parameter gamma is called the intensity of choice, and basically it drives the dynamics of the model. Some polar cases might be that this gamma is equal to 0, then we have the exponent of 0 divided by the sum of 3 exponents of 0, which is nothing else than 1 divided by 3, which is a stable proportion of agents who do not switch at all. On the other hand, if this gamma equals to or goes to infinite, there is a very wild switching. So each agent switches to the heuristic which is the most accurate. So the 100% of agents follow one of the heuristics, and other heuristics are not useful at all. And in some standard situation, the gamma is somewhere between these 2 polar cases. So positive between 0 and some larger numbers. What is extremely crucial for the next talk is that while the original standard Nuke engine model can be linearized and can be, for example, estimated via MLE, if this switching is introduced, the model becomes strongly nonlinear, it becomes completely analytically intractable, and some other ways of empirical inference or empirical examination needs to be suggested. If I should stress in a few points the contribution of our paper, the main contribution is kind of econometric or practical, because the paper, first and foremost, it offers a simulation-based estimation method, which can be used in general to any nonlinear macroeconomic model, not necessarily behavioral, but we focus on the behavioral models because we like those models. And via a elaborate Monte Carlo study, we show that this new simulation-based method is able to identify various behavioral parameters and various behavioral effects. One of the behavioral parameters and behavioral effects is this effect of this switching, which is driven by this gamma. And you see this is the exponential function. And I think a lot of has been discussed recently, unfortunately, about the dynamics of the exponential functions related to the recent COVID pandemics. So I do not have to stress that some even small changes in this gamma can have large consequences to the dynamics of these fractions, because everything is inside an exponential function. So a new simulation-based method, which seems to be able to well identify the switching parameter in the behavioral macroeconomic model, and also some other new behavioral parameters which have never been estimated so far. Technically, in terms of real econometric notation, we customize or modify the univariate simulated maximum likelihood estimator, which has been introduced to financial econometrics sort of a decade ago as well. And we modify this estimator and transfer it from the field of financial econometrics to macroeconometrics. So we allow this estimator from its univariate specification to be used to also the multivariate macroeconomic optimization problems. We discussed this paper actually a week ago with Kaz Holmes, and Kaz suggested that we actually bridge the gap between the macroeconomic laboratory experiments and empirical estimation efforts of behavioral Nuke agent models. So let's say that this can be kind of a more general methodological contribution of our paper. In the model, which I will very soon introduce, we estimate in various specifications of the model, we estimate between 4 and 16 parameters. I will only present 1 or 2 showcases in which we estimate something in between. I think it's 8 parameters estimation jointly. And then there is a empirical contribution, or because we are now in the agent-based model for policy seminar series, so also some policy-relevant contribution. We are able to pin down the behavioral parameters of the US economy, and especially what is important, we seem to be the first or one of the first to be able to really reliably identify that switching parameter, which drives the modal dynamics, the gamma, and we estimated around 1.4 for the US economy, which suggests that there definitely is a switching among the forecasting heuristics. It empirically validates the behavioral Nuke agent model, but this switching is rather less intense, kind of gradual, not very violent. The thing is, I suggested that we are one of the first, or maybe first, to estimate this switching parameter or the other behavioral parameters of the model, which I will shortly introduce in a couple of next slides. There are, of course, some related papers using some other more standard econometric approaches. One of the very appealing and already rather standard economic approach for agent-based models is the simulated method of moments. The pioneers of its application to behavioral Nuke agent model are Zhang and my co-authors Stefan Sacht. Then there is a set of papers trying to, or which successfully apply the Bayesian techniques. And also there is an attempt to apply indirect inference to the estimation of this type of behavioral Nuke agent model. If I can, I would suggest that neither of those, and there comes the contribution of our work, is able to, let's say, successfully or credibly estimate the switching parameter. I'm not completely sure why. In the papers by Zhang and Sacht, they simply calibrate the gamma, the switching parameter, to a few fixed values. In this Bayesian efforts, I can talk especially about Jakub Gracini, who presented a few months ago his new paper. I think it was also about Bayesian estimation, but something else. In his paper with co-authors from 2017, they tried to estimate that switching parameter gamma, but the posterior distribution is almost identical to the prior distribution, which basically suggests that the data does not really suggest anything interesting about that parameter. In this paper by Liu and Minford, they do estimate gamma, but they do not provide the confidence band or the standard error of this parameter. So we cannot know whether it's statistically significant or not. In all these, let's say, techniques, you have to make some potentially arbitrary decisions. For example, the set of moments in the method of simulated moments, the set of priors in the Bayesian estimation, or the auxiliary model in the indirect inference. The simulated maximum likelihood reduces to a large extent this potential arbitrariness of these approaches, which is one of its most important advantages. Let's jump to the model. This is something which will be very familiar to most of you, so I will not spend a lot of time with this. We have in its core a purely forward-looking Nuke agent model, which has a dynamic IS curve as an equation for the output gap, Nuke agent Phillips curve as an equation for the inflation rate, and monetary policy rule or Taylor rule. It is a purely forward-looking version, so it's very much simplified. We only have the expectations in here, and then the elasticity of substitution between consumption and saving, this tau parameter, which is the reaction parameter of output gap to interest rate and expected inflation. In the Nuke agent Phillips curve, the slope is labeled by kappa, and it's the reaction parameter of inflation rate to the output gap. And then we have two obvious clear parameters for the monetary policy rules, the reaction parameters to inflation and output gap. As I suggested at the very beginning, the magic of the model is that all these three shocks are IID, so they are normally distributed with different, potentially different standard deviations, but not autocorrelated. I will now be a bit more specific about the idea beyond the behavioral heuristics. The set of forecasting rules or forecasting heuristics follows the recent contributions of Kaz Holmes and the co-authors. And one of the original papers which, let's say, suggested these heuristics based on a set of learning to forecast experiments, and which provides a micro foundation of these heuristics based on laboratory experiments with human subjects, is by Michel Onufrieff and Kaz Holmes from 2012. These heuristics are not only micro-founded, but based on a large set of laboratory experiments. They are suggested to provide a best fit in both financial market environments, in some asset pricing experiments, as well in our Nuke framework. Have a look at the equations. So there are three heuristics actually in the paper by Holmes. There are four, but we simplify the setup a bit, and I will tell you how in a couple of seconds. Let's start with the first heuristics, the adaptive heuristics. The adaptive heuristics is parameterized by this parameter eta, and very simply it suggests that the expectation in time t about the output or inflation in the next period is somehow the weighted average of the most recent value and then the most recent expectation. So typical adaptive heuristics, a part is based on the previous expectation and the part is based on the new realization. The trend following heuristics, which is kind of obvious, it takes into account the most recent realization and then it extrapolates via the parameter iota based on the most recent change. So the difference between the most recent observation and the second most recent observation. In the original paper by Holmes, they actually have two trend following heuristics because it fits their data better. They have so-called weak and strong trend following rules, but both are based on the same, or both have the same equation, only the parameter which they calibrate is different. So for the practical estimation purposes, it's much better to only estimate, let's say, an average trend following heuristics. And then the last heuristic is so-called anchoring, or this abbreviation LAA stands for learning anchor and adjustment, because the idea is that the agents somehow follow the anchor, which is based on the sample average of all observations up to now. So this is a very stable term, plus the most current realization. So this is the anchor, which is parameterized by mu. And then from that anchor, which is very stable and follows the idea of a stable anchoring of the expectations, from this anchor, the expectation is extrapolated further again based on the most recent change. This is not the only menu of heuristics we could have considered. Actually, in the appendix, we have various alternative sets of heuristics and the results for them. One of alternatives might be, for example, fundamentalists and chartists, or very original optimists and pessimists by Paul de Grove from his original papers from the decade ago, or so-called strict fundamentalists and naive agents with respect to the output based on the most recent contribution by Paul de Grove and Ji. With respect to inflation, in all these alternatives, the agents are either extrapolators of the inflation dynamics or targeters who believe that the central bank is fully credible and that it will push the inflation always to the target. Then there is that switching mechanism, which I already explained at the beginning of my talk. So I will just reiterate on that, and I will be more specific with respect to some equations. But It's just what I have already said. So basically, the forecast performance of given heuristics, which are labeled K, so K for either adaptive heuristics, trend following, or learning, anchoring, and adjustment heuristic. I will call this anchoring heuristics for brevity. Are based on the mean square forecast error, which is nothing else than the expectations minus the reality squared. And I explain why there is minus, because the smaller the error, the better. Then there is the switching formula, which I already explained. We only, instead of mean square forecast error, use this U variable in here. And with that gamma parameter, which is important for the model dynamics and is actually the parameter which seems to be so challenging to be estimated so far. And then based on the fractions alpha, which sum up to 1, the aggregate forecast of the market is very simply suggested as a weighted average of the forecasts which are based on individual heuristics, these 3, and their fractions, which are based on their performance measure, on that accuracy. So this is the battlefield, this is the playground, this is the model framework, and I will again get back to that to refresh what the individual parameters talk about. I would now like to talk a bit about the method. The method which we introduced to the empirical macro is called simulated maximum likelihood estimation. And for univariate financial models, it has been suggested by Christensen and Shin in the Journal of Econometrics. And with my former supervisor, Joseph Baruník, we already adapted and applied this estimator to some financial agent-based models, still univariate, which has been published in JEDC. And what we do now is that we modify and we extend this estimator for macroeconomic estimation. In the original paper, there is a huge set of theoretical results which support or which prove the consistency and asymptotic efficiency of the estimator. So based on these theoretical properties, the estimator should deliver what we would like to be delivered. And one practical thing, which might be of an importance for practitioners, it does not require stationarity of the data. So it does not assume that the input data are stationary. They often are, because it's either an output gap or inflation and interest rates, but they do not necessarily need to be. A bit of equations, but I will try to be very brief. We have that behavioral Nuke engine model with the observables, which are the output gap, inflation, and the interest rate. We will label this triple of observables as a Z. Then the model is driven also by 3, the triple of random shocks. And theta, as usually, is the set of parameters which will be estimated and which are at the core of our empirical importance. This data generating process is based on the model function, which take into account the explanatory variables, the errors or the triple of errors, and the set of parameters, and simulates the model over time going from 1 to t. This data generating process has some conditional probability density, as any data generating process which we can think of. The problem is that we do not know the closed form solution of this probability density function, so we are not able to track this probability density analytically. If we are, we can standardly logarithmize the conditional probability density for each time t, then sum up to the log likelihood and maximize this log likelihood, which would give us the maximum likelihood estimator. The good thing is that although the maximum likelihood estimator is infeasible, because we do not know the formula for this probability density function analytically, we still have the model. We can simulate observations from this model, and via the simulations, via a simulation-based method, we can be able, or we are able, to non-parametrically estimate this conditional probability density based on Kernel method. How it is done, have a look. We will create this guy, which is based, or which follows the same idea as the data generating process, as the model function, with the only difference that this set of errors has one additional dimension. It does not only have the dimension of t, so it's not a triple in each time, but it has an additional dimension of n. And this guy, by definition, because these epsilons are taken from the same distribution as we assume for the errors, it follows, by definition, the target probability distribution, which we do not know. But, as I suggested, if we are able to simulate and simulate and simulate the data from the model, we are able to estimate, numerically estimate or numerically approximate this probability density function via a standard kernel method, in which we put this guy, the new guy, and then the original triple of variables, which are our empirical observables. Maybe a picture is worth 1,000 words. So this is a very simple sketch of what the method does, and it's simplified to one dimension only, to its univariate case. So imagine that we have a series in T. These are 4 observations going in T, and basically what any model does is that it takes the previous observations, it somehow predicts the next observation, and then the actual realization is the deterministic prediction plus some error. And unfortunately, we do not have the data for these errors. Of course, the closer the deterministic prediction to the realization, to the observation, the better for the practical application of the model. What the method does, it does not know the one single error which is taken into account in given t. This is basically the news or the innovation for given time, but it assumes its distribution, and we will assume this distribution to be Gaussian. What the method does is that it simulates a lot of realization from the distributions, these epsilons 1, 2, 3, up to n, and via these red points, it actually approximates the conditional probability density of this realization. Then we can use the Kernel method and put a kernel. Actually, let's think about the small kernels in each of these points, each small Gaussian distribution, which will finally numerically sum up and will approximate numerically this conditional probability density. If we have numerically approximated the conditional probability density, we can follow up the same idea as the MLE. So we can take this conditional probability density, which has been numerically estimated, and we can follow the same idea as MLE. We only do not have the functional version of the probability conditional density, but we have the numerically estimated version of the conditional probability density. Let's go to the results. So our main aim in the paper is to estimate the model parameters. In the showcase I will be presenting, the focus is on 4 structural parameters. So basically the reaction parameter of output gap to inflation and interest rate tau, the Nuke Phillips curve slope kappa, and then the parameters of the Taylor rule, and also the behavioral parameters, 3 parameters of the heuristics, and the gamma, the switching parameter. Here are some technical details about the setup. This n is important. This is actually the dimension of this kernel approximation. So we actually simulate 1000 of these red points to get the numerical approximation of the conditional probability density. We set the discount factor according to standard literature to 0.99. And the good thing is that for the kernel approximation, we do not only need to select the kernel, which we select as Gaussian, because of very reasonable idea which follows the central limit theorem. But we also need to select the bandwidth, basically the width of the Gaussian distribution, its standard deviation. And the good thing is that this is automated by so-called Silberman's rule of thumb, which provides the most optimal bandwidth based on a given data. Everything is computed in Julia, and the computational costs are quite large. Everything has been made manageable only based on parallel computation of a pretty strong server. So I will just briefly recap the structure of the model. So in the model, we have the structure which comes from the standard purely forward-looking Nuke engine model. So from which we are interested in the estimation of these 4 structural parameters. Then these expectation formation equations are the heuristics, which we have defined and discussed. So the adaptive heuristic, trend following heuristic, and anchoring heuristics. In this, we are interested in this eta parameter, iota parameter of trend following, and mu parameter of anchoring. And then everything is driven, the whole dynamics is driven by the multinomial logistic formula, in which we are interested in this intensity of choice gamma parameter, which, as we discussed, because it's hidden inside the exponential function, can have a really strong, and it has a really strong consequences to model dynamics, and it's crucial for the model stability, if somebody is interested in the analysis of the model stability. These are the results of the Monte Carlo study, because before we introduced the model to data, or the new method to data, we conduct a very large Monte Carlo study to be sure that the method works reasonably well. And these are kind of a showcase results. Here we have densities, sample densities of the pseudo-true estimation, because we parameterize the model based on the estimates of my colleague and based also on the of some calibrations by Kaz Holmes and his colleagues, and Paul de Grauwe and his colleague. And we are in the Monte Carlo trying to recover these pseudo-true parameters, which we have complete control about, to recover it back. So we know how the parameters are set, but the method does not know how the parameters are set. And these are the conditional, these are the densities of these parameter estimates of basically of the estimator for individual parameters. Of course, the object which we are talking about is 9th dimensional, because we are trying to estimate 8 parameters, and the 9th dimension is the likelihood. What is important is that to be able to read the results, the red vertical line is the pseudo-true parameter. The curve is the kernel density estimate of the sample density, and the bold black vertical line is the point estimate. So what we can basically see that except this tau parameter, the method is well able to identify the Taylor rule coefficients very accurately with no bias, to be honest. It is also well able to identify kappa, the Newton-Phillips curve parameter, and there is some bias for tau. We are not happy for that. We are able to explain that pretty well, and we provided details in the paper. But it is basically based on the structure of the model. Then the behavioral parameters are less well identifiable, but still pretty well in terms of its statistical significance. These dashed intervals suggest what is a 95% interval based on the sample of 300 random runs. So you see that it's never close to zero. So we are able to recover statistically significantly with no apparent bias, maybe some small bias for the anchoring rule coefficient, but for those who are somehow a bit deeper interested in the practical performance of various estimation methods, this is a very good performance. Most importantly, it is able to very well identify the switching parameter with no apparent bias and clearly statistically significant. These results are based on the sample length 500, and to give you some idea about the asymptotic efficiency with increasing sample size, this is a switch to a huge. In macroeconomics, this is unrealistic, but for the analysis of the features of the estimator, we need to go close to infinite. So basically, this is what happens if we multiply the sample size by 10, and you see that the everything narrows pretty much. So we observe the asymptotic efficiency of the estimator. Unfortunately, the bias for tau survives, and this is it. This is it. The gamma is pretty accurately identified. One more thing which appears in the results and which might be of interest for somebody who is interested in that dynamics or in that idea of simulated likelihood estimation. These are because we have the 10-dimensional beast. Our likelihood has 10 dimensions, so it's hard to be depicted on 2D slide. But what I can do is to depict the profile. So imagine that I have that simulated log likelihood and I cut it via a transversal cuts in the directions of individual parameters. So we see kind of a profiles of that simulated likelihood in the dimensions for given parameters. And what we see that the shape of the likelihood is very smooth. This is the average over 100 or over 300 random runs, very smooth, which definitely supports the optimization. It very often or almost everywhere leads to some unique global optima, which is also crucial for the optimization. For the behavioral parameters, the situation is a bit more complicated. That's why they are not so simply estimable. But again, at least in the average, it's very smooth. And also, if there are these kind of deviating realizations, they are also sort of smooth, even not so nice as for the structural parameters. The last but not least, the same holds for gamma. Yeah, for gamma, you see that the likelihood is very flat, so that's why it is challenging for many methods to identify the gamma. But you have seen in the results in here that even it is so flat, the method is able to identify it well. So if I have to sum up, the simulation maximum likelihood seems to be able to detect or identify the structural parameters well, except for bias for tau, which we can account or take into account when then aiming at empirical interpretation. Everything seems good for behavioral parameters, and we do a large, let's say, robustness check, or a robustness check. We apply reasonable parameterizations, which follow the parameterization in Holmes and co-authors in the Grauve, NG, also some other parameterizations from the papers of my co-author Stefan Sacht, and we also follow some alternative set of heuristics, which I talk about from additional papers. In all these versions, the method seems to show very similar performance. So we can suggest that it's very robust with respect to parameterizations as well as the actual sets of heuristics, because our set of heuristics is only one of possible from the literature. The last point will be devoted to empirical results. For most of you, this is the most important takeaway, I guess, but I would like to stress that these results are very limited, and we do not really understand this as something as a, let's say, clear policy advice, or we see this as a piece of a puzzle, which can, together with all other macroeconomic knowledge and all other papers related to the estimation of behavioral Nuke agent models and also standard macroeconomic nonlinear models, can bring some additional knowledge, which can be then used for policy advice, definitely. So I'm not presenting the best ever results, but I'm presenting what the method gives us for some specific empirical data. We only use US data. We did our best to have as large sample as possible, because the asymptotic features of the method favor large samples, of course. So we have the US data from 50s to 2019. We use seasonal adjusted real GDP for the output gap, which we filter via standard one-sided HP filter. Then consumer price index, again seasonally adjusted, and the effective federal funds rate for the interest rate. Two sets of results. In the first set, we estimate all 8 parameters of our interest. In the second, we fix these 2 because we are not completely happy with the results in here. The good thing on MLE as well as on simulated maximum likelihood is that the individual dimensions of the optimization can be to a large extent independent. So it does not mean that if one parameter is estimated somehow suspiciously, that all the estimation is suspicious. The other parameters can be and are actually to a large extent independent. So for the structural parameters, these 2 parameters are the parameters of the dynamic IS curve and the Nuke agent Phillips curve. They are, to our mind, suspiciously low, let's say, or not. With respect to kappa, not really low, but close to statistical insignificance, and for tau it's 0. For tau it's 0. So this is a kind of suspicious. What is important that the structural parameters of the Taylor rule make a pretty reasonable sense. It seems that based on our estimates, the central bank focuses much more on the inflation stability than on the output gap stability. What is the crucial output of our estimation are, however, these behavioral parameters. So this is the adaptive rule parameter, which is estimated 0.19, which basically suggests that the adaptive heuristics takes the current realization by 20%, and remaining 80% of the expectation is based on the previous expectation. So there is a slow adaptation, let's say, by 20% ratio, let's say. Then the anchoring parameter is estimated 0.3 or 0.31, statistically significant, which suggests that let's say the importance of the anchor with respect to the extrapolation from that anchor can be explained by the parameter 0.3, and gamma is, I already had this number in the preview, estimated 1.4, and what is much more important, it's statistically significant. So the statistical significant estimate of gamma provides the empirical validation of the behavioral Nuke engine model. And with respect to model dynamics, this is a value which gives rise to a rather less intense, smooth, gradual switching between these three heuristics. What might be interesting is that this trend following heuristics is estimated, or the parameter of the trend following heuristics is estimated 0, like complete 0, which basically means that the trend following heuristics does not really extrapolate. There are two reasons for that, or a story which has two reasons. The one reason is kind of technical, because you see that this term already appears in the anchoring heuristics. So it might be so that the additional parameter is redundant in the set of heuristics because the extrapolation is already contained in the LAA heuristics. The other reason is much more important from the macroeconomic point of view. Already in the laboratory experiments by Holmes and his colleagues, it is suggested very, very clearly that the trend following heuristics is only able to reasonably survive in the economic environment with positive feedback. And in the economic environment with negative feedback, the adaptive heuristics and the learning and anchoring heuristics drive the model dynamics. And the trend following heuristics does not really have almost any effect. So if we think about the US economy, especially when we have estimated some reasonable parameters for the Taylor rule, we would suggest that the central banks is able to keep the stability of both the inflation and the output gap, which means that the economy is characterized by a negative feedback, definitely not positive extrapolating feedback. And that's why the trend following heuristics has hard times to survive if the central bank does its job properly. So two reasons for this empirical result: one technical, based on the structure of the heuristics; one, let's say, macroeconomic theoretical reason, explanation. One more thing I would like to focus on is that if we fix these two, because we are not really completely happy with the estimates of tau and kappa for the all models, you see that except of some numerical, let's say, differences for the reaction coefficient for output, the other numbers are very similar. So the adaptive heuristics has almost the same estimate of the parameter, the same for the trend following, and a bit larger, but at a level kind of comparable coefficient for the anchoring heuristics. And most importantly, the gamma is estimated almost the same. What we also do is that we estimate the hybrid Nuke engine model, which is based on the rational expectations. The hybrid Nuke engine model, and I have to click in here, and I hope it works. has a bit more complicated structure because it takes into account the legs in each of the equations, and it has 3 more parameters. It has the parameter of habit formation high, then the parameter of price indexation alpha, and then the interest rate smoothing parameter phi r. But it does not have anything else. It does not have the heuristics, it does not have the switching, so it is just these 3 equations. And because it is completely linear, in fact, we can estimate this hybrid Nuke engine model also via standard MLE. So if we estimate these parameters, so we have a different set of parameters for the rational expectation Nuke engine model. If we estimate these parameters via MLE, we got the set of estimates. They seem to be much closer to something which you are used to, for example, from some standard calibration of the Taylor rule in macroeconomic models, as well as the strong interest rate smoothing parameter. But what is important, if we estimate the same model via simulated maximum likelihood, the numbers, the point estimates, are practically the same. The maximum likelihood is more efficient, so the confidence intervals are a bit more narrow, which is natural because this is a true maximum likelihood and this is simulated maximum likelihood, so it will be less efficient. But the point estimates are pretty much comparable. The only exception, small exception, is the reaction parameter for inflation, which is estimated 1.5 for MLE and 1.3 via SMLE, which on the other hand follows completely the estimates also for the behavioral model. This is it. If I should spend a couple of last seconds of my talk via a short conclusion, I would like to sum up that we are the first who apply the simulated maximum likelihood estimator in macroeconomic optimization, and we estimate the parameters of a very appealing behavioral Nuke engine model. We test the properties and the feasibility and the quality of the estimation output of this new estimator via Monte Carlo study, which gives us a very favorable results and answers. And we are able, via this new method, identify significantly the switching parameter for the US economy, gamma, which we estimate around 1.4. And because the estimate is statistically significant, together with the statistically significant estimates of some additional behavioral parameters, this altogether provides a strong empirical validation of the behavioral Nuke engine model of the kind we are suggesting. This is all. I will be very much happy for any comments, any critical discussion. I am ready for that, so go ahead, no problem. And thank you very much. Thank you very much for your attention. I expected it will be shorter, so I am sorry that it was not.
Thank you, Jiří. Floor is open for short questions. Anybody?
So I have a question. Actually, it's 2 questions. So first of all, thank you for the presentation. It is very interesting. So my first question is about the sampling methodology for thetas. Could you explain a little bit what methodology did you use? Something like brute force or something else? I don't know. And the second question, it's regards the methodology. It seems to me that this methodology, this estimation methodologies, shares some similarities with the Bayesian estimation proposed by Grazzini and co-authors. what would you say is the main difference with respect to their approach, and what, in your opinion, drives the performance, the difference in performance between your and their methodology? And that's it. Thanks.
Okay. The first should be simple to answer. The second is much more for discussion. So basically, for the sampling of that, you talk about the sampling of the errors or of the
the parameter vectors. So the vectors of parameters.
This is basically a very standard gradient-based optimization approach in Julia, where we do all the optimization. This is labeled BFGC, and it's a completely brute force. So it's based on the random repetition of the same process with different random numbers. The results which I have suggested are based on 300 random runs. So basically, the optimization parameter searches over the parameter space based on the gradient descent, and this everything is in that brute force manner, repeated again and again and again to get these densities for the estimator actually. So that there is nothing really, let's say, sophisticated on this sampling method. It's based on the brute force random generation of random data sets, or random data sets of that errors and that guys which are taken from the same distribution of errors, but have that one additional large dimension for the approximation of the conditional density. And then a very standard, in this situation, gradient based, because you see that we have pretty smooth shape of the criterion function. So even very simple methods which are standardly used for optimization of or in any field can be used. We experimented with several algorithms for the optimization. This seemed to be one of the basic, but providing very reasonable performance. We also experimented with some we also experimented with the most simple ones. For example, the Nelder-Mead algorithm, which does not provide so nice results. It works, but it does not provide so nice performance. And we also experimented with some genetic algorithms or differential evolution algorithms, which also provide kind of comparable results. So this is perhaps the answer for the sampling distribution technicalities. The other question which requires a comparison to Bayesian estimation techniques is a bit more difficult. We try to do our best in the paper to talk about this in a few paragraphs, because this is kind of a crucial thing. I would suggest that the simulated maximum likelihood is somewhere in between the typical frequentist approach to empirical estimation and the Bayesian approach to empirical estimation. It shares the idea of the distributions, but in the Bayesian estimation, you simply have to set the priors. You have to select these priors, define them analytically, and then you let the data talk, and you see how the posterior deviate from the prior, what the data tell you about the parameters which are beyond this distribution. In simulated maximum likelihood, we do not have to do any of this potentially arbitrary decision, because the method approximates the distribution of the parameter itself. It's in the core of the method, this approximation of the shape of the distribution. So that's one thing, but you are completely sure, or you are completely correct, that the notion beyond that is sharing is sharing some aspects. If I should stress some, let's say, advantages and disadvantages of the method compared to Bayesian estimation, and similarities. So let's start with the similarities. The similarities are the computational costs, because both the convergence of the Monte Carlo algorithms as well as the computational demandingness of our approach is pretty large. So this is similar. Our method does not require the potentially arbitrary choice of the prior distributions. On the other hand, it requires some potentially arbitrary assumption about the distribution of the errors. So basically, we assume that the errors are Gaussian, that they are normally distributed, which comes from the idea of central limit theory, which suggests that if the error is basically the sum or average or whatever of various effects, which can have various distribution, which we do not know, its sum will tend to be normally distributed. So it's a reasonable assumption, but it has to be done. And on the other hand, for the Bayesian estimation, you can directly estimate this parameters of these, for example, the standard deviation of the errors. Perhaps this, I would rather see that these are kind of complementary approaches. What we can see if we compare the papers, especially if we compare the paper of Jacob Grazzini with this paper of ours, the main difference is that we are able to give you a bit more empirical inference about that switching parameter. Why, to be honest, I am not sure, because like my understanding is that this is a combination of the smooth shape of that likelihood function, which really supports and favors the optimization. And yes, perhaps there is another comparison which really deserves attention, and it is comparison to the simulated method of moments, which to some extent shares also the brute force idea of the sampling distributions, and it can work based on the very same algorithmization of the optimization. But typically for the method of simulated moments, the criterion function is very rough, so it has multiple local minima, and it is far from being smooth. And we experimented quite a lot with the same model framework, with the same heuristics, but with SMM and SMLE. And you typically see that because of this shape of the criterion function for the moments, you are not really able to identify this switching parameter. But because of the smooth shape of the simulated likelihood, which is inherited by the kernel density estimation, I believe this is the game changer, which is able to identify the switching parameter, which, as you have seen, has otherwise very flat likelihood. So some standard optimization techniques cannot be able to distinguish the difference. Under the brute force and enough computational power, we are able to distinguish this. Hopefully I answered.
Yeah, thanks.
So we are a bit tight with time, so I think we need to close it here. Let me just announce the next seminar, which will take place on April the 8th, and it will be given by Ben Smedo from the Central Bank of Hungary, and it will be about the heterogeneous effects of macroprudential policy on the Hungarian housing market. So thanks everybody, and thanks Jiří, of course, and have a nice rest of the evening.
Thank you very much. Bye-bye.
Thank you. Bye.